Welcome to my talk on a framework called NIFTy. It is an acronym for Numerical Information Field Theory. In this talk, I would like to motivate why we felt the need to build yet another AD toolkit framework. And in doing so, I would like to show you that it's rather easy actually to do so yourself in your working in a higher level language. Okay. I'm going to take a slightly different angle at AD because by heart and by profession, I'm an astrophysicist. So I'm looking at pictures like these. You can see a reconstruction of the 3D distribution. Oh, sorry, I can maximize the screen. You can see here the 3D distribution of interstellar dust within our Milky Way. These kinds of reconstruction have on the order of tens of millions of parameters, and we have huge statistical inference machineries to get those kind of images or reconstructions. Luckily, those statistical models, in the end, how we optimize them is just the minimization of a very, very big cost function. And cost functions are way easier to optimize for if you have gradients. I would like to briefly discuss the specifics of our cost function. Bear with me, this is going to make sense, and this is going to explain why we're interested in AD and why we needed our own AD toolkit. So our cost function, which I'm going to denote by H, has the following shape. It has a term called L here that denotes the log likelihood of our problem, that couples the parameters P and the data D, and then some regularization P prime P. Most, if not all, inference problems can be rephrased in this picture. It really depends on the kind of problem that you're tackling, whether that's a suitable picture for you. You can often further reformulate this equation by identifying a function f, a deterministic function f that takes in those parameters, and then your log likelihood just couples the output of f to the data, and then you still have the same regularization. With pen and paper and some statistics, if you have this kind of cost function, you can derive a suitable approximation to your second derivative, so to your Hessian. And in specific, you can derive a second order, like the approximate Hessian that is positive definite. So that's very convenient for optimization purposes. The Hessian has then the following form. It has the Jacobian of your function f in it, denoted here by JF, some simple matrix L, and the Jacobian of f again, plus a unit matrix. This cost function together with your Hessian already screams like you want to do second order minimization, and this is exactly what we're going to do. Second order minimization means that you're going to take a gradient once, then you're going to scale that gradient with the inverse of your Hessian. Since we only have the Hessian, not the inverse Hessian, you're going to use implicit methods to apply the Hessian over and over again to get the inverse of it. And after achieving your scaled gradient, you then take a step. This scheme tells you that you're going to call this approximate Hessian a lot more times than you're going to call your gradient. And as you might know, this is already kind of unsuitable for most AD toolkits because they think about making the gradient call fast or making the forward pass fast, but they don't think about making the Jacobian adjoint and the Jacobian fast. This is a slightly different picture. And NIFTy is built all around this idea. It is a DIY AD toolkit to make this version of the Hessian fast. So to make the Jacobian adjoint, the Jacobian fast to apply. Plus then there's a bunch of statistics. I would like to derive how we build our AD toolkit from a simple example. I would like to think about our function f, which we usually call model, in terms of an exponential function and a weighted reduction. The weighted reduction here is just an implicit, very large matrix that somehow weights our various inputs and then yields out an output. In order to get a fast Jacobian, or our our approximate Hessian, we want to skip in the Jacobian all the nonlinearities. So in contrast to doing a normal forward pass, which you would do to get the Jacobian, we don't want to reevaluate any of the exponential functions in the course. Furthermore, we don't want to duplicate any memory if it's also used for the Jacobian adjoint path. So we want to be as memory efficient as possible, since our parameters are going to be very big and every kind of constant that we're going to encounter is also very big, and we don't want to store anything twice if it's not strictly necessary. Furthermore, we also want the user to be able to easily configure the gradients or the Jacobian calls if the user thinks he has a better idea of how to solve it. So those are our 3 main objectives that we want to solve. And our approach to do so is a concept called linearization. You can think of a linearization in NIFTy as just being a weird term to say Jacobian. We think of a linearization as being a triplet of three things, namely the primals, so the vector at which the linearization is constructed. Then one function that evaluates the Jacobian path of our linearized function, and one to evaluate the Jacobian adjoint. We're going to use P as to denote the primals and T to denote the tangents, and also the cotangents. How we do that in NIFTy is by simple operator overloading or dispatching. So we're going to, for every call, for every individual function, and basically NumPy, provide our own custom linearization. So for the exponential function, we would introduce an additional branch into our exponential function that if we're going to be called on a linearization, we're going to get another linearization that amends the linearized exponential function to it. So how this looks like in code is, instead of just mapping an operator up to, instead of just applying an operator up to the primals, we have a branch in the operator, depending on if the primals or linearization input is just a normal primals vector, no linearization, we're just going to call it itself. If it is a linearization, however, we're going to, again, call it on the primals vector, here denoted by PLP, and additionally construct a linearized version and the adjoint of the linearized version. So we're going to linearize our operator, add the position PLP, and then multiply times the linearized version that is already part of the linearization that we're getting in. So we're applying the chain rule as part of our overloading strategy. For our specific example that we wanted to tackle, this means that for the exponential function, we're going to get a Jacobian that is just a simple diagonal operator. So this is just a multiplication. And our weighted reduction, since this was just an implicit matrix, is just the implicit matrix itself. The Jacobian of any linear operator is just the linear operator itself. So in total, we can write down the full Jacobian of our function f. It's just going to be the Jacobian of the exponential function evaluated at the input p, and then times the Jacobian of the weighted reduction evaluated at the exponential function p. So we're propagating the new primals position through our Jacobian. And the transposed is just a transposed of the left. In terms of code, the class that we built around this likewise takes 3 inputs. It knows about the primals, so it knows where the linearization is built. It knows about the forward pass, and it knows about the backwards pass. Here denoted by FWD and BWD. If we're going to call our linearization, we're going to say that this is just the Jacobian applied, and if we're going to call the T, so the transpose of it, we're just going to swap the backwards and forwards, so we're going to call the backwards pass of it. With this simple class, we can already start building our overloading strategy. So our new exponential function then has this branching in it. Namely, it's going to check whether the input is a linearization. And if it is not, it is just going to apply the normal exponential function. In this case, just calling NumPy exp. However, if it is a linearization, we're again just calling numpy x, but this time on the primals of the linearization. And then we're going to amend the forward pass by multiplying our new linearized version of x times the already existing linearization PL. And for the backwards pass, we're going to call the transpose of our linearization times our new Jacobian of the exponential function. So this already applies the chain rule within our overloading. And this code actually already works. If you copy the definition of the linearization class and this exponential function, you can run this code in the bottom and should hopefully see sensible results. Likewise, for our weighted reduction call, we're going to first check whether we have as input a primals or a linearization. If it's not a linearization, we know that we're just working with the raw numpy arrays or array class. And we're just going to apply some very weird things here. We're just going to weight our input, our reshaped input, sum it, and then put it into a new array called y. Those weights you should imagine are super expensive. I just use numpy ones here, but but in practice there are some very complicated function of some additional input that is not shown here. Since weighted reduction is a linear operator, the forward pass is just the linear operator itself, and we can refer back to the function itself and apply it to the linearization and just immediately get the Jacobian of it. So it's very straightforward to implement. And again, this code runs. If you want to test it, copy over the code on the bottom here. With the overloaded exponential function and the weighted reduction, and in NIFTy there's a bunch more, we can now start building our model that is going to be just the exponential function and the weighted reduction. And by doing this chain rule in the overloading, we already have the full Jacobian of our model. Right, so to connect back to our original problem, we wanted to have this, we wanted to optimize this cost function, and we wanted to do so using our approximate version of the Hessian. Since we already have our function f, we can just now concatenate f with all the various other things, so with our likelihood and penalization from the prior, and retrieve our overall cost function. Here I assumed that our likelihood, log likelihood, is just a Gaussian, and this gives you then the following shape. If you want to retrieve gradients, you already have everything you need because the gradient is just the Jacobian adjoint of your function h. So you can just pass into h a linearization at p and apply it to 1. This will give you the gradient of your cost function. And you can retrieve the Hessian, or our approximation to the Hessian, likewise by propagating the primals through f to get the Jacobian, and then you're going to use the Jacobian transposed and the Jacobian with this additional term r prime plus some plus the unit matrix, and give that back as a Hessian call. Now we're not going to reevaluate the linearization of f over and over, since we're only going to pass the primals once to f and then going to reuse that Jacobian in the minimization. With these building blocks, we already achieved everything that we set out to achieve, namely we are comparatively fast. Of course, that depends on whether the individual computations are fast. Fast here, I mean just in the sense that we're skipping nonlinearities and that we are implicit. We're not building up full Jacobians just to transpose them. And we're also memory efficient, or at least we incentivize being memory efficient by always building the adjoint and the non-adjoint part in parallel. So if the user recognizes that he can share memory between both passes, it's very straightforward to do so because you can just refer in something from the outermost function via closures. And we're also customizable because the only thing you really need to do to define your custom Jacobians is you need to have one if clause in your forward pass that checks whether your input is a linearization, and then you have to amend it, and that's already it. Right. OK. Here we'd like to take one small detour and briefly talk about checkpointing, because that's also very important for us. As I mentioned, we're going to work with huge parameter spaces, and we can't afford storing anything twice that's not absolutely necessary. Since this trade-off between having to store everything versus having to reevaluate everything is in general not possible to do for an AD toolkit, we just rely on a lot of user input to do that. Our default strategy is to just apply the overloading for all the individual operators. But as I said, if the user wants to, he can just build his own Jacobian and thereby potentially save memory. So how this looks in practice is for the weighted reduction. I mentioned that this is this huge matrix. If you would just naively try to build a Jacobian of it, you would apply those weights to your primals vector. So what normal AD toolkits would do is they would notice that something constant is going to be applied to your input, and they would store this constant and memorize it. But we want to avoid that. We want to compute it on the fly, which is why we had this weird weighting here. And we didn't just recompute all the super expensive weights outside of this loop. Since we are very much configurable, you can just implement your join pass of that and also recompute the weights in the join pass, and thereby potentially save a lot of memory. The idea here being you just take this code and transpose it manually and pull in the weights into the loop itself in order to not store them. In practice, this looks then slightly different in NIFTy, but the overall core concepts of linearizations and them being fast, memory efficient, and easily configurable still holds. The same model in NIFTy would look something like this, where you have your input x. It's going to be exponentiated, and then you have this weird weighting. Actually, this was a rebuild of something we call a line of sight response. And this would be your model, and you could get the Jacobian of your model by passing in a linearization into f. Right. With this, I would already like to conclude. I hope that in this talk I was able to convince you that linearizations are very neat for tackling second-order minimization strategies, and that building your own AD toolkit is actually pretty easy. At least if you do it in NumPy.
Okay, thank you. Are there any questions? I'll start in the back.
Are you doing anything special to guarantee that the Hessian is positive definite, or your approximation, does that already guarantee that it's positive definite?
Yes, so are we doing anything to guarantee that our Hessian is positive definite? The answer is yes and no. So by construction it is. So what we're doing here is we have the Fisher metric for the likelihood, and then we use the curvature of this regularization term as the Hessian for P prime P. The Fisher metric is by construction always positive, or this approximation to the Fisher metric is by construction always positive definite, because the Jacobian is positive semi-definite. Sorry, this decomposition of J prime J is by construction always positive semi-definite. And if you then add something that is positive definite, namely this unit matrix here, you always achieve something that is positive definite.
Is that similar? That kind of looks like a Gauss-Newton solver. Is that more or less what's going on here, or is that a different solver? Because I believe in Gauss-Newton they have a similar approximation.
Sorry, can you repeat that question? I didn't get the first
Gauss-Newton looks like a Gauss-Newton solver, but I'm not sure.
So this is very similar. So what we're doing here is at each stop we're going to approximate the curvature locally using some kind of Gaussian approximation, if you want to think of that in those terms. This is very much consistent with our minimization strategies, because basically all second-order minimizers assume that locally you can describe your cost potential with a quadratic function. So we're kind of doing what is in very good agreement with the minimizer, namely we're going to approximate the curvature also using a second-order approximation.
Are there any constraints on what the L function should look like, or can it be an arbitrary nonlinear function?
you can derive how the function L should look like for a specific likelihood. Bunch of statistics and some calculations are going to tell you, if you have your Gaussian likelihood, what the L prime tilde is, what the L tilde is supposed to look like. So for Gaussian likelihood, L would just be the inverse of the noise covariance. And often in practice, the noise covariance of your Gaussian is going to be diagonal, so it's very easy to invert.
I have another question over here.
Yeah, I was just wondering, so what optimization algorithm are you doing Newton-Raphson? And if so, are you, it wasn't clear to me whether the matrices get assembled or not, whether the Hessian is getting built explicitly or
sorry,
not.
no, we at no point build the Hessian explicitly.
So you only do vector products? And
Yes, we only apply the Jacobian. We're going to, in our model, we're going to successively amend the function that applies the Jacobian. We're never building explicitly the Jacobian.
Okay.
That's why we track the transpose of it and the original function, because we cannot just transpose a matrix. This is because the parameters would be, let's say, 10 million have 10 million dimensions, and the output of F also would have 10 million dimensions. 10 million squared doesn't really fit onto a computer anymore.
Okay, thank you, and let's thank the speaker again. If there